Hello, welcome to Circuit Lab, practice number 10, Kirchhoff's voltage and current laws, Wheatstone bridges, Thevenin's theorem, and Norton's theorem. My name is Mr. Burleson, and you can reach me at geaux15@hotmail.com. Multiple sources. Sometimes a circuit has more than one source. Voltage sources should be added in series, and current sources should be added in parallel. Never put a voltage source in parallel with another voltage source, and never put a current source in series with another current source, as it can violate the circuit rules and create a problem that can't be solved. Kirchhoff's voltage law. Remember, this is for division C only, but it's useful for division B. The directed sum of the electric potential differences around any closed network is zero. So basically, the sum of voltage in any closed loop is equivalent to the sum of the potential drops in that loop. In other words, if I go all the way around from one point all the way around back to that same point, and I add up all the voltages and subtract out all the voltages that are inverse polarity, it will equal zero, no matter how many loops. So if I look in the two examples to the right, if I go between around from the lower left hand corner here from 0 all the way around and through R1 and back, that tells me that VB minus the voltage of R1 equals 0, or VB is equal to the voltage of R1. Okay, I can also do that same loop starting at the same 0, but now going through R2. I go through the voltage of the battery around through R2 back around, and so VB is also equal to the voltage of R2. Or I could do the loop of just the resistors, and I go from the 0 underneath R1 up, and so that tells me that the voltage of R1 is equal to the voltage of R2, and they're all equal to VB. Okay, now if I look at the other diagram where I have a voltage with two resistors in series, the voltage of the battery, VB, if I start from the 0, I go up to that, is equal to the voltage of R1 plus the voltage of R2. So if I take both of those voltages and add them together, it equals to VB. So you just look for the loop. So a KVL, if my battery in this particular case is 9 volts, okay, and I've got 3 resistors, and the voltage of R1 and the voltage of R2 are both 3 volts, what's the voltage of R3? Well, it's got to be 3, because the voltage of R1 plus the voltage of R2 plus the voltage of R3 has to equal the voltage of my battery per KVL. So therefore 3 plus 3 plus X equals 9. Subtract 6 from both sides, and the voltage of R3 is equal to 3 volts. Now let's make that voltage 12 volts for the battery, and I'm going to make R1 and R2 equal 5 and 3 volts respectively. What's the voltage of R3? It's 4 volts, because again, 5 volts plus 3 volts plus X is equal to 12 volts. Subtract 8 volts from both sides, the voltage of R3 is equal to 4 volts. Now let's look at the one where V battery is equal to 15 volts, okay, and voltage of R1 is equal to 7 volts, and the voltage of R2 is equal to 8 volts. What is the voltage of R3? It's 0 volts, because the voltage takes 15 volts is equal to 7 volts plus 8 volts plus VR3 volts minus 15 volts from both sides, and VR3 is equal to 0 volts. And that could happen very easily if the resistance is 0 in R3. Another KVL, okay, if voltage is 9 volts in the battery, what is voltage R1 and what is voltage R2 in the upper example? And the answer is they're equal to 9 volts, because no matter how I draw the loop, V battery is equal to VR1 is equal to VR2. Okay, now if I do the bottom series parallel one where V battery is equal to 9 volts and VR1 is equal to 3 volts, what is the voltage of VR2 and VR3? Well, it's 6 volts for both of them. So between 2 and 5 and between 3 and 4 nodes, you have the same voltage, and it has to be 6 volts because 6 plus 3 is equal to 9. Okay, now if I do the same thing and I say, okay, if V battery is equal to 12 volts, what is VR1 and VR3? Oh, well, see, this is a little trickier. So VR1 would then be, I'm going to do the big loop, or I'm going to do the internal loop, and it's going to be 9 volts. Okay, so VR1 is equal to 9 volts, and VR3 is equal to VR2 if I do the loop on the far hand right side, so it's 3 volts. So Kirchhoff's current law, KCL, and again division C, but very useful for division B, means that any node, the sum of the currents flowing in is equal to the sum of the currents flowing out of that node. So just think about it this way. Every charge that goes into a node has to come out somewhere, okay? Or it has to be canceled out. So in other words, all the current flowing in has to equal all the current flowing out, okay? Now, this is very, very useful when you're doing nodal analysis. So before we did loops, and now we're going to do nodes. So if I look in the case of VB, R1, and R2 on the left-hand side there, the I total is equal to the I1 and the I2 because whatever current I have coming out of that battery is split between R1 and R2. And by that same token, that means that the I1 going into R1 has to equal the I1 coming out of R1, and the I2 going into R2 has to equal the current coming out of R2. And then they get recombined, and I1 plus I2 equals IT at the bottom. Okay? Now, it's really simple in a series circuit because everything's just got I total. There is no I1 or I2. Okay, and so the voltage coming out of the battery has to equal the voltage going into the battery, and the voltage going into each resistor has to equal the voltage coming out of each resistor. And since there's no other path for it to take, the current has to be the same throughout the entire system. So if I1 is equal to 9 amps and IR1 is equal to 3 amps, what's IR2? Well, IR2 obviously would have to be 6 amps because 6 amps plus 3 amps would be equal to 9 amps. Okay, well, what's I2? Well, I2 is always going to be equal to I1 in this case because the current flowing out of the battery has got to equal the current flowing into the battery. So therefore, it is equal to 9 amps. The second one, I1 is equal to 9 amps. IR1 is equal to 6 amps. So IR2 is now 3 amps and I2 is still 9 amps. And then the last one, I1 is equal to 10 amps, IR1 is equal to 4 amps. IR2 then would have to be 6 amps, and I2 would again be 10 amps. Believe it or not, you can just do it as a dot. You can show the node as a single dot and show the current going in and out. So, in this particular case, I'm using a KCL, I can say that I1 plus I2 plus I3 has to equal I4. Okay? All the ins have to equal all the outs. Now, I can reverse the direction of any of those arrows and it's still valid. It's just that now what would have been a positive current will now be a negative current and vice versa. So, if I1, I2, and I3 are all 9 amps and that's all my inputs, I4 is going to be 27 amps out. If I1, I2 are 5 and 4 amps and I4 is 3 amps, well, I've got 9 amps coming in, I got 3 amps going out, so I got to have another 6 amps coming in. So I3 would have to be 6 amps. Okay, now if I1, I2, and I3 are 9 amps minus 9 amps and 7 amps, what's I4? Well, the ends are now 9 minus 9 plus 7, which equals 7. So therefore, I4 must equal 7 amps. Now, in this particular case, I1, I2, and I3 are all going in. So 2 amps minus 9 amps plus I2 is equal to 9 amps. So 2 minus 9 is minus 7 amps. So we add 7 amps to both sides, and I2 is 16 amps. And let's see if that makes sense. 16 plus 2 minus 9. So 16 plus 2 is 18, minus 9 is 9 amps. So that makes perfect sense. Now, a Wheatstone bridge was an electrical circuit that was used to measure unknown electrical resistances by balancing two legs of a bridge circuit. One leg which includes the unknown component. Okay, so it was invented in 1833 by Samuel Christie, but the person who's named after is Sir Charles Wheatstone, who improved upon it in 1843. So they used to use it a lot for the purpose of soils analysis and comparison, because you're comparing it, and you would have very, very high precision resistors, because they used to could measure voltage real easily, but it was much tougher to measure resistance. So remember, if the bridge is balanced, R2 over R1 equals Rx over R3, or you can do R2 R3 divided by 1. Well, R2 is equal to 300, R3 is 200, so that comes out to 60,000 divided by 300 is equal to 200 ohms. Okay. You could also notice that the ratio between R1 and R2 was 1, so therefore the ratio between R3 and Rx would be 1 as well. Okay, now we've got a little bit more difficult of a problem. Okay, R1 and R2 now are 100 and 300 ohms, and R3 is 200 ohms. Okay, it's balanced, so therefore Rx would be I almost made a mistake, 600 ohms. And the reason why you can tell that is that the ratio is always going to be the same. So now let's talk about Thevenin's theorem. Thevenin's theorem says that any combination of voltage sources, current sources, and resistors with two terminals can be electrically equivalent to a single voltage source and a single series resistor R. So I could take as many voltage sources and current sources and resistors in the most complex network, and I could replace it all with a single voltage source and a single resistance. This is used a lot, because remember, we were talking about driving circuits, and I want to know what the internal resistance is. Well, the internal resistance is the Thevenin resistance. And I want to know what the drive voltage is. Well, that's going to be the Thevenin voltage. Okay. So how do we find these things? So first, you need to calculate the output open voltage. So in other words, pretend that A and B is completely open. There's no load resistor. So it's infinite resistance, and you find what is the output voltage. This is the Thevenin resistance. Then you calculate the output current when the output is short circuited. So the load resistance is 0. R Thevenin is equal to V Thevenin divided by this IAB. Or you can replace all the independent voltage sources with short circuits and all the independent current sources with open circuits, and look back in from A to AB and find the equivalent resistance. Okay, now you say, well, which one should I use? Whichever one's easier to do. So let's look at this game. I want to find out V Thevenin and R Thevenin. Okay, so in this particular case, if A and B are open, so no current's going to flow through R1. Okay, so I've got a very simple current, or I've got a very simple voltage splitting problem where I've got a 15 volt source with a 2 kilo ohm resistor and series with two 1 kilo ohm resistors. So therefore VAB is equal to half of 15 volts is equal to 7.5 volts. Okay. All right. So that was actually pretty easy for me to figure out. I didn't even need a calculator. Okay. Now you see on the left hand side how you would do it with a calculator. Now let's figure out what's the equivalent resistance if I just take out that pesky voltage source. Remember, I can replace it with a short. So now I got 1 kilo ohm, and I've got 2 kilo ohms in parallel with 2 kilo ohms, which comes back to 1 kilo ohm in series with that top 1 kilo ohm R1. So it is 2 kilo ohms is my R Thevenin. So R Thevenin is 2 kilo ohms. V Thevenin is 7.5 volts. And I did that all without a calculator. Now Norton had a theorem that says that any collection of voltage sources, current sources, and resistors with two terminals is electrically equivalent to an ideal current source in parallel with a single resistor. So you have an I Norton and an R Norton. Okay, so it's sort of the inverse to. So to find that, calculate the output current when a short circuit is put across A and B, and that will be your Norton current. And you find the Norton resistance the same way, okay? So you can either calculate the output voltage when in an open circuit condition, okay? And then you divide that by the you can divide VA by I Norton, and you can come out with the R Norton, or you can do the same thing as you did with the Thevenin, where you replace independent voltage sources with short circuits and independent current sources with open circuits. So let's do the same thing here. Okay, so if I short AB, okay, so I've got 1 kilo ohm in parallel with 2 kilo ohms in series with 2 kilo ohms. Okay, so what you'll find out is that my current, if you look off to the left, comes out to 3.75 milliamps. Okay, then if I remove the voltage source and do the same sort of looking back from A to B to find the equivalent resistance, it still comes out to 2 kilo ohms. Okay, now one thing that you probably noticed real fast is, wait a second, that I Norton was the same current that we found when we were looking for Thevenin, and R Norton was the same R Norton as R Thevenin, and that is correct. So R Norton will always be equal to R Thevenin. V Thevenin will be equal to I Norton times R Norton, and I Norton will be equal to V Thevenin divided by R Thevenin. So you can use whichever one makes the problem easier to solve. Make sure that the current source and resistor are in parallel for Norton, and make sure the voltage source and resistor are in series for Thevenin. So again, I want you to do a practice quiz, but this time I want you to bring it back and only do it for 30 minutes. Really stress yourself. See how well you do. Again, update your binder. Now I want you to do level 10 resistors, level 11 Wheatstone, and level 14 Norton Thevenin. Correct the problems you missed on the practice competition on a separate piece of paper. Thank you. This has been Practice 10.